Hi everyone. Today, the topic of my talk is Introduction to Three-Phase Circuits. In this video, I am going to tell about why do you have to study about three-phase circuits, what are the advantages of three-phase circuits over single-phase circuits, and what are the applications of three-phase circuits in electrical machines and power systems. All of you would have seen this one. This is a common sight in everyone's homes. So this socket basically is a single phase supply socket. So one terminal is going to be phase, the other terminal is going to be neutral. And the voltage which is coming across these two phases is 230 volts 50 hertz supply. For higher capabilities or for higher capacities, we use these two terminals. And these terminals are called as earthing terminals. They are generally used for protection. If at all a short circuit occurs, the current passes through the earth and the human being is being protected. Else, there is also a chances of leakage current through which the earthing is going to protect us, or the leakage current passes through the earth because the earth has very low resistance. So this is all a single phase supply socket which has 230 volts frequency and 50 Hz standard frequency. And this is the representation of a single phase voltage waveform, which is just a sinusoidal waveform. It has positive peak and negative peak, and along with the time, and the frequency of this frequency of a cycle is 50 Hz. So this is represented in a form of circuit like this. In industry, it is just represented like this, as if we can plug and connect our devices. Here is a basic device which everyone knows. So these two terminals stands for the connection of phase and neutrals, and this is being connected to the mobile to charge the battery. As the input is AC here and the output is going to be DC, this particular part is called as adapter, where it converts the AC, the phase neutral, the AC voltage is being converted to DC voltage. This DC voltage is used to charge the battery which is in the mobile. This all happens with a single phase supply, and this is a common view for every one of us, where whenever we see an electric pole, there are three wires connected everywhere. These three wires stands for three phases. These three phases are called as three-phase system. So each phase is called as RYB. It is also called as ABC or 1, 2, 3 or XYZ, PQR. In some industries, it is also called as UVW. We'll study more about three-phase circuits later. And this is the waveform of three-phase circuits. You can see phase 1, phase 2 and phase 3. These are the three phases. You can see in phase 1, it starts at 0, goes to a maximum value at 90 degrees as like a normal sinusoidal waveform, and goes to 0 degrees at 180 degrees, and at 270 degrees it goes to its minimum value of -1, and at 360 degrees it goes to 0. This is one of the phase which acts like a normal sinusoidal waveform. Look at this phase 2, which is in red in color. It starts exactly at 120 degrees and goes to a maximum value after and completes its positive half cycle and goes to negative half cycle as like a sinusoidal waveform. Look at the third phase, which is blue in color. It starts exactly at 240 degrees and it behaves as like a sinusoidal waveform with positive half and negative half. If you look at all the three waveforms, they carry maximum value of +1 and they carry maximum value of -1. And if you observe them more clearly, they are all sinusoidal waveforms. One is starting at 0 degrees, the other one is starting at 120 degrees, the third one is starting at 240 degrees. So if finally we can conclude from these things like, so they are all equal in magnitude, but they are being displaced by 120 degrees. So this is how a three-phase waveform is going to occur. If you look at phase 1, this voltage waveform is represented by V1 is equal to Vm into sine omega t plus 0 or minus 0, or V is equal to Vm into sine omega t is its representation because it starts at 0 degrees. Now coming to this red phase, which is phase 2, this I'll call it as V2. V2 is equal to Vm into sine omega to minus 120 degrees because it starts after 0 with a difference of 120 degrees. Now I come to the phase 3. This phase 3 is starting at 240 degrees after 0. So this phase 3, V3 is called as Vm into sine omega t minus 240 degrees. As we all know, minus 240 degrees is equal to plus 120 degrees. Therefore, this phase 3 is also called as V is equal to Vm into sine omega t minus 240 degrees, or V is equal to Vm into sine omega t plus 120 degrees. So finally they are all equal in magnitude but displaced by 120 degrees. The phase difference between A and B, the first phase and second phase, is 120 degrees. Between phase 2 and phase 3 is going to be 120 degrees. Again, between phase 1 and phase 3 is going to be 120 degrees. So totally they complete 360 degrees, which is one complete rotation. And this is how it is represented in any electrical equipment as RYB. And there are going to be a three-phase waveforms, voltage waveforms, current waveforms, load are going to be present. Basically, it is represented like this, which means that they are operating with a three-phase supply. So this is a common site for everyone, which is occurring near to a colony or to a apartment or some villa. So these transformers are called as distribution transformers, where they get 11 kilovolts as the input supply, and they are going to step it down to 400 kilovolts, and it is all in three phase. This 400 kilovolts is going to be divided into each phase, and we are going to get 230 volts. You can see 3, which is nothing but 11 kilovolts is coming as input here, and it is going into 4. You can see the 4 wires, which has R, Y, B, M. So R and N is going to give 230, B and N is going to give 230, C and N, B and N, R and N is going to give 230, Y and N is going to give 230, B and N is going to give 230. So the single phase is produced from three phase, and there is a relation between the line voltages and phase voltages, which will study in the near future. And this is also one of the example of the distribution transform. So this is the basic animation, how the power moves from source to the load. Here we have a star connected source or a three-phase source RYB, and this one powers the load, which is also a star connection. This is the load, which is RYB. They're all connected. The power moves from source to the load. So this is a star connection, which is only a three-wire connection. From three-phase alternator, it is being connected to the three-phase load. And now let us come, why do we have to study about three-phase circuits? In this unit, it starts with three-phase circuits. Why? What's the purpose to study about three-phase circuits? What are the advantages of it over single-phase circuits is being studied in this unit. Phase sequence, I am studying about R, Y, B, A, B, C, 1, 2, 3. Why can't it be R, B, Y? Why can't it be something like 1, 3, 2? So what makes the phase sequence to come in certain way is being done by phase sequence. And the advancement of this topic is in power systems, which is nothing but the sequence impedance. Later we have three phases. How do you interconnect them and make it as star and make it as delta? In star, we still have three connections. If a wire is connected from the neutral point, it is called as three-phase four-wire system. If wire is not connected, then it is called as three-phase three-wire system. And after knowing about interconnections, we are going to study about what is the relationship between their voltages and currents. So we are going to derive few equations from the phasor diagrams, like what is the relationship between line voltage and phase voltage for star connection, line current and phase current for star connection, line voltage and phase voltage for delta connection, line current and phase current for delta connections. So these derivations play important role in dealing or analyzing the problems of three-phase circuits. Later, we work with the problems based on three-phase circuits which has balanced loads. So what is meant by balanced loads? So balanced loads are something like whenever equal impedance or resistance is connected to each phase, then it is called as balanced load. Suppose in the R phase, I have 10 plus J12 ohms. Similarly, in the Y phase, if I have 10 plus J12 ohms, and B phase also I have 10 plus J12 ohms, then it is called as star balanced load. So this balanced load can be either in star connection or it can be in delta connection also. Now coming to the unbalanced circuits, this unbalanced circuits, as the name says, the load is not same as like balanced circuit. Each phase carries its own load. Then we are going to analyze this unbalanced circuit as like whenever it is connected in delta, whenever it is connected in star with 4-wire system with neutral and 3-wire system without neutral. So this is a basic example where we have three-phase AC supply which is being connected to a star net, star load, and from the neutral we have a wire. So this is called as 4-wire system. So this is your basic three-phase waveform which has a maximum value of 10 and minimum value of -10. You can see the RYB colors here. And after measuring all the voltages current, we are going to deal about measuring the three-phase circuits, measuring the power in the three-phase circuits. The measurement of the power can be done by 3-watt method, which is actually has more disadvantages. Later we study more detail about 2-watt meter method. This is very important watt meter method because by using 2-watt meters, we can measure the total active power in three-phase system, total reactive power in three-phase system. We can find out what is phi, the phase difference between voltage and current in three-phase system. By that, we can find out cos factor, which is cos phi, which is nothing but power factor of this system totally. So we measure the power by mostly 3-watt meter method. And these are the basic applications of the three-phase system. This is your transformer core, and you have windings. You have 3 windings. So this is a three-phase transformer which carries low voltage winding and high voltage winding with its corresponding insulations. This is an animation picture of a three-phase transformer core, and this is a physical picture of a three-phase transformer core. So you can see the windings here, three-phase windings with the tapping connections. And this is how the total transformer is being completely done. And these are the bushings which carry your RYB. These are the bushings which carry your three-phase supply RYB. So this is the complete picture of your completed transformer with the inserted core and windings. And this three-phase transformer are also used in power systems. So this is the generating station, and this voltage is being stepped up in order to reduce transmission and distribution losses. And it is being, whenever you can see, this is all three-phase supply. The total transmission distribution is done with three-phase supply, and it is being stepped down and it is being given to your household industrial applications. So here it is all three-phase supply is being employed for either generation, transmission, distribution. Utilization varies, whether if it is a domestic load, we use single-phase supply. Few agricultural loads are also of single-phase supply. Many industrial loads are of three-phase supply. And this is the one which you are finally going to study. This is the mind map of three-phase circuits, unit 2 of network theory, according to Jain to Hyderabad syllabus. So in the introduction, so basically what you are going to study is advantages of three-phase circuits versus single-phase circuits, comparison between single-phase circuits and three-phase circuits, how do I write the voltage equations and current equations for three-phase circuits, phase sequence, how it is being generated, and how are the phase sequences can be varied, but what is the importance of the phase sequence. In the interconnections part, you are going to know how to connect between star connected network and delta connected network. And after that, we are going to study in detail about star connected network, writing out the circuit diagrams, and from that we get the phasor diagrams. From the phasor diagrams, we are going to derive the relationship between line voltages and phase voltages, line currents and phase currents. In the similar way, we work with the circuit diagram of the delta, derive the phase diagram from the circuit diagram, and we are going to derive the relationship between line currents and phase currents, line voltages and phase voltages. On top of it, we are also going to study what is the total active power in three-phase system, reactive power and apparent power in three-phase systems as well. So now later we are going to come to unbalanced circuits. So this is all dealing with the balanced part. Later we study about dealing about unbalanced circuits. When you talk about unbalanced circuit, there is a procedure for each and every interconnections. If it is an unbalanced delta connection, we go according to the procedure. We derive line voltages, phase voltages, line currents, phase currents, and the total power, total active power, total reactive power, total apparent power. Similarly, draw the phasor diagrams. When we deal about unbalanced three-phase wires, we go with the procedure and derive all the line voltages, phase voltages, line currents, phase currents, and all the powers. And when we deal about 4-wire star connected system, it is being dealt by 3 methods. One is by Kirchhoff's law method, the other one is neutral shift method, the third one is star to delta transformation method. After converting it to delta, it is being done according to the unbalanced delta connected load. Finally, after calculating all the voltages, we are going to draw the phasor diagrams for all the unbalanced system. Next topic of the three-phase is wattmeter methods. What are the different wattmeter methods employed to calculate active power, reactive power, apparent power, phase angle phi, and also power factor? So we mostly concentrate on 2 wattmeter method, which is the most advantageous method. So from the circuit diagram, we get the phasor diagram. From the phasor diagram, we derive what is the total active power. Later we derive what is total reactive power, and later we find out the phase difference phi between the voltage and current, and after that we can calculate the power factor of the circuit. So with this, the three-phase circuits for the network theory is going to be completed. So thank you all.